Okay, one more video for this lesson. Provide the two positive integers that add up to 40 and have the largest possible product. Okay, so step one is to figure out what the objective function is. That's the one that you are going to be finding the derivative of, which means that's the one that you need to find the maximum or minimum of. In this case, we're trying to find the largest product of two integers. So that would just look like x times y. I called it s. I don't really have a name for this side. It's just, I don't know. I think I picked s for some. I don't know. It doesn't matter. The left side here doesn't matter so much. It's more, this is the product, and we're going to need to take the derivative of that side, set it equal to 0, things like that. So whatever you want to call that left side is fine. Okay, so let's talk constraints. Because again, our objective function has two variables in it. We need to somehow make it so there's only one. And we were given that two of the integers add up to 40. Those two different integers add up to 40. So now we can solve for one of those variables. It doesn't really matter. I solve for y, and then you can go back and plug it in. So now our objective function looks like x times 40 minus x instead. And then if you simplify it, because we're eventually going to take the derivative of that. Okay, so let's talk domain. Domain gives us the largest and smallest and largest possible values for x. So again, x can't be, it's positive integers. So really, x shouldn't equal 0, but 0 would be the smallest it could be, because technically that's an integer. It's debatable on if it's positive or not. The largest would be if y was 0. If the second one was 0, then x would be 40. So our domain's from 0 to 40. So if x is 0, that's the smallest it could be. If y is 0, that's the largest it would be. Okay, let's take the derivative, which is just 40 minus 2x. Set that equal to 0. And then find your critical point. In this case, it's 20. And now, at this point, I showed this last time. This is where you could, make your first derivative test and plug numbers into the derivative equation. Doesn't matter what numbers you pick. Like, it literally doesn't matter as long as it's within the range. And then you test to see that you have a maximum, which means you're plugging this number in. This would be 40 minus 2 times 1, and then 40 minus 2 times 39. And then you're showing that the tangent lines are up and then down, which means there's a max. So that's the first derivative test. It's not too bad. I like the second derivative test, which is where you find the equation for the second derivative. And then based on whether it's concave up or concave down, you can say that it's a maximum or a minimum. So if it's concave down, meaning that the second derivative is negative, and in this case, the second derivative is always concave down, so at x equals 20, it's going to be concave down, and x equals 20 is where there's a horizontal tangent line. Okay, so this proves there's a maximum. Since the second derivative is forever negative, our function's concave down, and that proves that there's a maximum. So x equals 20 is one of our positive integers, and now you just need to find the other one. So go back up to your constraint and plug in x equals 20. And now you get y equals 20. So there's your final answer. Okay, let's do one more. What is the area of the largest rectangle with lower base on the x-axis and upper vertices on the curve of y equals 6 minus x squared? Okay, so here's the situation. Here's the curve 6 minus x squared, and we have a rectangle with a base on the x-axis and the upper vertices touching the graph. Okay, so this is really the only scenario that we can have where the rectangle is centered right there at the origin, because otherwise we can't have that. Like this vertice is not touching. So the only scenario that we can have here is a rectangle that's centered right here on the y-axis. But we just don't know what size it is. Like it could look like this. It could look tall and skinny. It could look really skinny. It could be short and wide. So we just don't know. We just know that it needs to be symmetrical here because it has to be centered right there in order for the two upper vertices to be touching like that. Okay, so what's the objective function this time? Question is asking for the largest rectangle. I'm sorry, the area of the largest rectangle. So we're going to have an area function that we need to take the derivative of. Well, the area of a rectangle is length times width, or base times height, however you want to say it. Again, two variables there. We need to replace them. So there's only one. So let's talk constraints here. Notice that from here to here represents some x coordinate. Like we don't know what it is. I mean, it could be 5 or 3 or whatever, but it's an x value. And because of the symmetry here, from here to here represents the absolute value of whatever this number is. And I say absolute value because we're talking, distance. The fact that it's a negative x value right here, like this point right there would be negative x. That's not really what we need right now. We need length as a distance, so it's positive. And then our height is going to be f of x. It's going to be whatever the y coordinate is on this vertical line. And again, we don't know where it is. Like I said, like the rectangle could be like this, and the height's right here. So we don't know. We just know that it's going to be this y coordinate. Okay, so our constraints are going to be the length is 2x because it represents two distances of x. And then the height is f of x. So if we plug that into our area function, we have 2x times f of x, and f of x is actually 6 minus x squared. So here's our area equation for any rectangle. And now I distributed here because the next thing we're going to do is take the derivative. Let's talk domain first. So smallest it could be, again, is 0. If x is 0, we've got like a straight line and a point right there. The largest it could be would be if this point here was down here, and then we would have like a horizontal line. So if this point is right here, then that means this is 0. And if that's 0, then x is equal to the square root of 6. And again, it's positive because we're talking about the largest it could be. So our domain would be between 0 and the square root of 6. Okay, let's take the derivative now of our area equation, which is going to be 12 and then 6x squared, power rule. Set this equal to 0 to find the critical value. Going to add that 6x squared, divide by 6, and then we end up with the square root of 2. Ignore the negative. And at this point, this is where you can do the first derivative test and stick your critical point in there and plug a number in. I'm going to use the square root of 1, which is just 1, the square root of 4, which is 2. Oops, stick that over here. And so plug in a 1. Right there, you get 12 minus 6, which is a positive number. Plug in a 2 right here. You get 12 minus 24, which is a negative number. So that does prove there's a maximum because the sign of the derivative changes from positive to negative. Again, that's the first derivative test. If you want to use a second derivative test, you find the second derivative, which is just going to be negative 12x. You plug in your critical point into the second derivative, and it's a negative number. So if it's negative, that means our function is concave down. So that means that the critical point is a maximum. Okay, so we have found our x coordinate. that causes the largest rectangle to happen. So the next thing you need to do is find the area using that x-coordinate. So you just plug in. We have 12 times square root of 2 minus 2 times the square root of 2 cubed. We get to simplify this a little bit. The square root of 2 cubed is the square root of 2 times itself 3 times. 2 of them makes this. So just the square root of 2 cubed is really 2 times the square root of 2. And then we're going to multiply it by this 2. So this ends up being 2 times another 2 from this, and then 1 left over square root of 2. We end up with 12 square root of 2 minus 4 square root of 2, which is 8 square root of 2. So it's approximately 11.314 units squared.